Now let's look at the second question. And so here we have a Python code for the solution and some explanation. So let me look at the Python code for the solution first. Right? So what is wrong here? So first, notice that these parentheses are unnecessary. So another thing is there is this notation for the adjacency matrix that is A underscore W. And I don't really understand what the purpose of that is. So isn't it better to use just A? Because then it would be consistent with whatever we have had before, right? So it doesn't really change anything. So if you replace A underscore W with A. Okay, let's go further. So then here we have A equals A3 equals A cube, and then num is A3 over 2 is the diagonal. But why can't we do it in just one operation without explicitly using this new matrix, which is A3? Okay. Yeah, so it works just as well. So then there is kind of there is an issue here. So here x is the vectorized version of the factorial function. So first of all, what is wrong with it is that using x for a factorial is just is very counterintuitive. So it's hard to understand. Because when I read it, so I think that x is a vector or a number, but now that this is a function, which is actually a factorial, it doesn't really make much sense. So I would rather call it vectorized factorial or something like that, or just factorial, because NP math factorial is already there. Well, but another issue is why should we do it at all, right? So because the whole purpose of this applying to this function x is the following. So here in this line, denom equals something. What it actually does, it calculates it applies the function that takes basically a calls times a calls minus 1 over 2. So it applies this function is like f of x equals x times x minus 1 over 2 to every entry of the vector a calls. But you don't really need to a vectorized version of the factorial to do that. So you can just do it right away. I understand that the purpose was probably to avoid issues with factorial of 0 and factorial of 1. Because factorial of 0 is 1 and factorial of 1 is also 1, but if we do it like this, then the result is going to be 0, and then it's going to lead to indeterminate forms like 0 over 0, and then we have to take care of it. But still, taking care of those things is, I think, more natural and more reasonable, and definitely is going to be much more efficient than vectorizing the factorial function. Okay, so let me explain how to do this. So this denom is actually nothing else but a calls times a calls minus 1 over 2. Well, however, if I do it like this, so notice that I get this mistake. Shapes 1, 7 and 1, 7 are not aligned. This is because a calls, the type of a calls is not an array but a matrix. And then when I use this star, it interprets it as a matrix multiplication. And what we need is an element-wise multiplication instead, right? So which means that what I should do, I should convert it to an NP array. So now it works. Well, however, it does not always work. So let me set p to be smaller. Sorry. 0, 5, 4. No, somehow it does. Sorry, yeah. No, it does work. Yeah. So I thought that it works because there is this um, uh, extra assignment. So if the degree of a vertex is 0 or 1, then it is just artificially changed to 2. So this is to prevent issues with division by 0. So that has been taken care of. So which means we don't really need to do anything else. So this is a full solution. So now it is correct. So now it's a good solution. So, however, there are some issues um, with the explanation, right? So try to read it. Using the adjacency matrix AW, calculate AW cube first and store it as A3. Well, look, why do we do it at all? I mean, so first of all, here you're just explaining what the code does, but you kind of explaining it literally. So instead of helping the reader to get the intuition behind the code, you're just explaining what a particular line of code does. So which is not really necessary, right? So it's better to just get rid of it. But then so we can just delete it. So another thing is that in this our whole text, there are some issues with formatting. So the chunks of kind of Python comments are not highlighted and LaTeX equations are not highlighted, right? So let me do it first. So at least it's going to be formatted and it's easier to understand. X is the number of edges. Oh, by the way, in this text, X is the number of edges connected to the corresponding vertex, which is the degree of a vertex. And in the code, X was the vectorized version of the factorial function. So it is, it's really hard to understand solutions when that there is such a mess with notation. Well, anyway, so now we at least fix the formatting. So let me write. So the diagonal entry of A, so now we change it to a cube. So it's just the diagonal entry of a cube is the number of pairs of vertices that are connected by an edge for corresponding vertices. Well, it doesn't really make much sense, does it? The number of pairs of vertices that are connected by an edge for corresponding vertices. So what is corresponding vertices? What do these vertices correspond to? I mean, I know the solution, so I understand what the students who wrote it had in their head. I understand what is meant here, but I know it because I understand it because I know the solution. So for an external observer, it would be impossible to understand it because you read it and what is correspond. So what do these vertices correspond to? So let me show how you can fix it. So the diagonal entry of what is actually meant here is that the diagonal entries of a cube, so they are indexed by vertices of the graph, right? So we could write something like the ith diagonal entry of a cube is the number of pairs of vertices that are connected by an edge and are connected and are both connected to vertex I. Now it is clear. So the ith diagonal entry of a cube is the number of pairs of vertices that are connected by an edge and are both connected to vertex I. Okay, so let me look at the next sentence. Then calculate the denominator, which is all combination. Well, first of all, there is a combination, that there is a spelling error of pairs of vertices for any vertex. Well, again, it doesn't really make much sense, does it? So which is all combination? So calculate the denominator. So the denominator is a number, and at the same time they say that this is all combination. Well, it's probably all combinations, so it should be plural. So okay, all combinations of pairs of vertices, but still the denominator is all combinations. It doesn't make much sense. So what is meant here is that the denominator is the number of all combinations of pairs of vertices for any vertex. But it's still wrong, because what is claimed here is that we have a set of pairs of vertices, and all combinations, if you understand it literally, is the set of all subsets of the set of pairs of vertices. So it doesn't really make much sense, right? So this is actually what is meant is the number of all pairs of vertices for any vertex. But how are these vertices related to this vertex? It's not explained. So what is probably meant here is to calculate the denominator, then calculate which is the number of all pairs of vertices connected to the given vertex. Well, let's just reuse the I, because we are denoting it by I. So now, I mean, now it's not in Shakespeare level of English, but it's at least it is understandable. Okay. This is done by summing the columns of the adjacency matrix. Okay. So of the adjacency matrix, well, we have renamed it to A. Then calculating the number of combinations by, well, but this is actually just the n choose 2, right? So instead of doing this, we could write a binomial coefficient binom x2, and it is very well known that this coefficient is just x times x minus 1 over 2. Okay, so now it's better. Where x is the number of edges connected to the corresponding vertex. Well, first of all, corresponding, is a wrong choice of words, so it's given. And second, the number of edges connected to the given vertex has a specific, name in graph theory. It's the vertex degree, where x is the degree of the given vertex I. All right, so now, okay, it's not perfect, but it is still readable. If you do it like this, it is understandable. So when you are typing a solution to a problem, please remember that someone else has to read it, and try to imagine that you are someone else, and try to read it as if you were someone else. So is your text understandable by another human being or not? And if it is not understandable by another human being, then try to rewrite it so that it becomes understandable. So that's the main takeaway from this exercise 2.